Thank you, Jacob. So today I will be discussing our project entitled Safely and Effectively Communicating Non-Connected Vehicle Information to Connected Vehicles. I will go over an introduction, the objectives of this project, a literature review, the feasibility analysis we did, the experimental design in the driving simulator, the results of the experiment, and the conclusion. The number of people killed by drivers running red lights have hit a 10-year high, and in 2017, 939 people were killed by vehicles running a red light. This number is the highest death toll since 2008, and it's 28% higher than in 2012. Each day, there are 2 people killed in the US by drivers running the red light. Connected vehicles can increase highway safety by taking advantage of the sensors, the information received from roadway infrastructure, and information from other vehicles. And in fact, we have countless hypothetical safety improvements that we can use from the connected vehicles, such as receiving information about icy conditions and crashes, and also receiving information about a potential red light runner. So, arguably, we can say that in-vehicle sensors, they should be able to detect a potential red light runner and communicate this message through the sensors of in-vehicle sensors and the transportation infrastructure to connected vehicles. However, these sensors, they can be victim of blocked lines of sight due to the presence of other vehicles, pedestrians, roadway infrastructures, and hence, these can create a blind spot scenario. So for example, if we take a look at this image, we can see a driver. He has the green light, and then because of the building at the corner, he's not able to see that someone was running the red light, and hence we have a crash. So how can we mitigate this? So for this project, we had 2 objectives. First, we wanted to evaluate an approach that can be used to communicate data from a radar-based vehicle detection to connected vehicles using basic safety messages, which is BSM. And we want to explore the feasibility of using radar-based vehicle detection systems to supplement information available to connected vehicles, which includes the communication of a potential non-connected red light running vehicle to connected vehicles on the other hand. And second, we wanted to evaluate the effectiveness of an advanced warning message in the form of audiovisual warnings that's gonna be done in the driving simulator. And we want to communicate the presence of a potential non-connected red light running vehicle from a blind spot, as we can see in this figure. So, for the second objective, we did that in the driving simulator, and we collected data about the reaction to the warning system from the participants of the experiment. Before starting our experiment, let's do a small literature review. So in recent decades, humans have relied on their vehicles as the main mode of transportation. However, driving is a complex task, and it requires full attention and awareness. However, because the drivers are prone to making mistakes because of a human physical, perceptual, and cognitive limitation, we have human errors in driving. And in fact, driver error has been identified as the main cause in 75 to 95% of roadway crashes. Around 40% of these crashes are happening at intersections, and non-compliance with traffic control devices is one factor contributing to such crashes, with the red light running being a frequent cause at signalized intersections. As I mentioned earlier, recently we had 939 fatalities. Usually red light running are causing an estimate of 165,000 injuries and around 800 fatalities each year. Half of these fatalities are pedestrians and people in vehicles that are hit by the red light runners. Now, the market for in-vehicle systems has grown in the past years, and several in-vehicle displays have been tested for both commercial and research application. The most common types of in-vehicle displays are head-up displays, head-down displays, and augmented reality. So head-up displays, as you can see in this figure, they project the needed information directly on the windshield, which is the line of sight of the driver, and hence the driver gets the required information without taking their eyes off the road. Head-down displays, as you can see in the figure, in the bottom figure on the left, they are located in the middle of the control panel of the vehicle. And even though they are useful for navigation, for example, drivers have to take their eyes down the road to be able to see this message. Augmented reality, they are most advanced forms of head-up displays, and they are currently the most advanced technology on the market. And they can project lane departure warning, automated cruise control, blind spot monitoring. They can do a lot of things. So Continental, which is one of the leading manufacturers of head-up displays, is supplementing vehicles such as BMW, Mercedes-Benz, Audi, and others with head-up displays. And they have been used to convey speedometer data, navigation directions, roadway speed limits, warning at specific sections of the road. So some of the advanced driver assistance systems now available in current vehicles, they include a collision warning system, which monitors the vehicle speed and the speed of the vehicle in front of it and the distance between these two vehicles. And if the vehicle is getting too close due to the speed to the rear vehicle, the collision warning system will go on, like as you can see, it's a beep and some dots on the windshield. And in this case, the driver can be warned about an imminent crash. Vehicle equipped with blind spot information system, they get help when a driver is detected in their blind spot when they are changing mirrors. And like a dot can be shown on the mirror, and it depends on the location from which side the driver is passing by, the dot would be shown on the left or on the right. So in-vehicle technology has grown over time, and it continues to improve. And several studies have examined the effectiveness of such systems. And they have used the driving simulator to evaluate these systems, as the driving simulator is a safer and more economical method than on-road testing. So for example, the driving simulator has been used to test drivers' compliance with the speed limits when supplemental information from in-vehicle systems were present. Another study, for example, has used the driving simulator to evaluate driving behavior using in-vehicle traffic advisory systems. The picture you can see is an augmented reality windshield-based in-vehicle navigation system that's gonna show the direction of navigation to the driver. All these studies showed the effectiveness of such warning systems. Now, one of the objectives of this project calls for exploring the feasibility of using radar-based vehicle detection systems to supplement information available to connected vehicles, which includes communicating an unconnected potential red light runner to connected vehicles nearby. So rather than waiting for every potential red light runner to go and buy a connected vehicle, we can use radar-based vehicle detection systems to allow providing messages to connected vehicles using the infrastructures to nearby connected vehicles near the intersection. So radar-based vehicle detection systems, they are underused components in the transportation system infrastructures, but these detection systems are typically installed at signalized intersections to monitor the presence of vehicles within a predefined zone by emulating loop detectors. But they also have the capability to continuously track the position and speed of vehicles approaching an intersection. So the position and speed are key components of the basic safety messages that can be received by a connected vehicle through technology like direct short-range communication. Through a software-based approach, radar-based vehicle detection systems could be used to mimic a connected vehicle and send non-connected vehicle information to nearby connected vehicles, and hence we can increase the effectiveness of market penetration of such technology. So to test the messaging communication between the traffic signals roadside equipment and the vehicle onboard equipment, we did the following steps. We had an onboard unit installed in a demonstration vehicle. We also had onboard equipment, which included a tablet equipped with vehicle-to-infrastructure messaging software. It was also installed on the demonstration vehicle. And then we drove that vehicle through the intersection to verify signal phase and timing, and basic safety messages were received and transmitted. And the result of such tests are shown in the following three figures. So the first figure shows these lanes in blue. They are the map message, and we can also see the head of the signal, and we can also check their phases and their current location on the demo car. Over here in the second photo, we can see the vehicle's basic safety messages pinpointing the precise location of the vehicle. We have the latitude, longitude, the speed, the elevation. We have all these information. And in the final figure, we can see the current signal phase based on the processing of signal phase and timing messages received from the roadside equipment at the intersection. So for example, in this one, we can see that we have a red signal, and in 6 seconds, it's gonna turn into a green light. Now, the flow on how everything is happening is as follows. So first, we have a non-connected vehicle, which is detected by the radar-based vehicle detection at the intersection. Then the location, the speed, the heading, it's all monitored by the radar-based vehicle detection. And then the intersection processor receives this information called TDCS messages, as well as the current signal phases. And then the algorithm running on the interaction processor determines if the vehicle is in a state where the red light signal is likely to be violated. An intersection collision avoidance (ICA) message is developed and provided to the roadside unit for transmission. The RSU transmits a message frame, including the ICA message, to onboard units in range. The connected vehicle onboard unit picks up this message, and the intersection collision avoidance message is processed in tandem with the connected vehicle's position, speed, and heading on the onboard unit processor to determine if the safety message should be communicated to the driver or not. And if the message is needed to be communicated, then the safety message is provided to the vehicle and it's displayed in the vehicle. Now, for the driving simulator experiment, we tested the effectiveness of a warning system. So we used the full-scale Ford Fusion driving simulator located at the University of Wisconsin-Madison. Participants, subjects, they can interact with this simulator and they can drive as if they're driving in a real car. The simulator can project a virtual world, and we, in addition to speed data, we were able also to collect position, lane position, steering angle, brake pedals, gas pedal position, along with other variables. So the scenario involved an urban roadway cross sections, and the speed limit was set to 35 miles per hour. The driving was conducted with the simulator set to emulate normal weather conditions, day driving, good visibility, no rain or snow. The drive was 2.5 miles long, and we split that into 3 small runs because of concerns of simulation sickness. And each run took on average like 144 to 209 seconds. The warning message was displayed on the windshield, and it was an audio-visual warning system. The drivers were able to see this message on their windshield. This one means that a red light runner, like someone is crossing from right, and if someone was crossing from the opposite side, the icon was flipped. And these cues were triggered based on a randomized experimental matrix that we already defined prior to doing the experiments. Now, when the driver was driving and the distance to the stop bar pavement marking was 0 or 50 or 100 or 100 feet, those were our different treatments, the audiovisual warning system was triggered, and the driver was able to see the previous icon. Now, this is a video taken from inside the driving simulator when someone was driving. So as you can see, while approaching the intersection, you see the warning message popping out. There was also an audio, but unfortunately we can't hear that. And then it's up to the driver to decide what they want to do after seeing this message and hearing the beep. So in this case, they didn't come to a complete stop. They just reduced their speed a little bit, and they were able to avoid a crash. So we had participants placed into a control group and treatment groups. The control group received the warning system at the stop bar, while the participants in the treatment groups received the warning at 50, 100, or 100 feet before the stop bar pavement marking. And we randomly placed the subjects into each of the 4 groups, and 25% from the subjects were assigned to each category. 20 subjects were recruited to participate in our experiment. We had 10 males and 10 females. They had an average of 32 years old, and the range was between 19 to 75 years old. All subjects were licensed driver. They had between 1 and 52 years of driving experience. They all had normal to corrected to normal vision, and they had to react to 9 non-connected vehicle running red light runners events, and they were distributed all over the 3 runs, and they were randomly placed. Now, when participants started with the practice session before taking the experiment, none of them had simulation sickness. But once we started the actual experiment, we had our oldest driver and our youngest driver drop out after the first run because of simulation sickness. We also had another participant drop out after finishing the first run, and 2 participants drop out after finishing the second run. And in total, we were able to collect 154 experimental data to do our analysis. And in addition to our main task, which is just like a drive, we had a secondary task where we asked participants to click on this push button whenever they saw a pedestrian, and we placed this push button on the steering wheel. And this is a Bluetooth connected device, so we were able to collect data using an Android platform device phone. Now for our results. So each driver reacted differently when they were exposed to an imminent collision scenario with a red light running vehicle. And this figure shows the location of the reaction from the stop bar when each driver was approaching each event. And similarly, these two figures show the location of reaction from each side of travel by the red light runner. Now, when a driver was approaching the signalized intersection, the warning system was activated, and when they reacted, that was called the reaction time. However, in some cases, when the warning system was activated at the stop bar, as you can see here, the driver reacted to the red light runner rather than reacting to the warning system itself. So in this case, the reaction time was taken as a negative value. It's more like we calculated the reaction time from the moment the activation system was there. So in this case, we have negative values. And that's why you can see them most likely when a warning system was activated at the stop bar. Drivers were able to see the red light runner prior to having the warning system activated. So they reacted to the event itself rather than the warning system itself. And these figures show our data after removing the outliers and having everything identified. Now, as you can see, our data was not well normally distributed, so we weren't able to use the typical ANOVA and t-tests, but we were able to use the non-parametric equivalence. So for example, we started with a Kruskal-Wallis test to compare the reaction time means across the 4 groups. And with a very small p-value, we can see that there exists a significance between the reaction time at the different locations of activation. We can see that the reaction time when the warning system was activated at the stop bar was 0.05. That's because we had so many drivers reacting to the red light runner itself rather than to the warning system. But it was 0.9 seconds to 1 second for the other 3 events. With a small p-value, we then conducted a pairwise Mann-Whitney-Wilcoxon test to check which groups have statistically significant difference. And as we can see, we saw a statistically significant difference between the stop bar and the activation at each location. And we also saw that we have one between the 50 feet activation and the 100 and the 150. Similarly, for each location, from each direction of travel of the red light runner, we conducted a similar statistical test, and we had similar results. After conducting the pairwise comparisons, we saw that there exists a statistically significant difference between the stop bar and the activation at the stop bar and the other 3 locations. Now, speed profiles were also plotted for each subject, and in addition to the speed, we also shown when the warning system was activated. As you can see in this figure, for example, on the left, the warning system was activated at the stop bar. As you can see, the driver reacted before even receiving the warning system, and that means they reacted to the event, to the red light runner itself. While the other figure, it shows when the system was activated at 50 feet. And as you can see, after getting the warning system, the driver reduced their speeds, and then they reacted accordingly. And as you can see, drivers reduced their speeds, and they reduced it on average between 2 to 3 seconds. So they didn't have to come to a complete stop. They only had to reduce their speeds a couple of miles per hour, and that would have resulted in a safe non-crash event. However, some drivers, they did come to a complete stop. Also, this is for each direction to travel, and it's consistent with the previous results. Some drivers did come to a complete stop, and as you can see, drivers, they come to a complete stop for around 30% at the stop bar, for like 17% at the 50 feet warning activation, 30% at the 100 feet, and 50% at the 150 feet. Now, because we don't want our drivers to come to a complete stop and cause rear-end crashes in this case, we can easily say that it's safer to have the warning message activated at the 50 or 100 feet. As for our secondary task, we can see that we had several pedestrians crossing, so we were expecting drivers to see 7 pedestrians in the first run, 2 on the second one, and 4 on the third one. And on average, people were able to detect 70% of these pedestrians. And it means that drivers were more focused on driving, and they only detected, like they only paid attention to pedestrians whenever necessary. So when pedestrians were crossing, or when pedestrian caused a specific event that they had to react to them. In conclusion, we can say that in-vehicle technology has improved over time, and these advancements have led to the inclusion of active safety systems that can help drivers avoid collisions. And in this experiment, we used audiovisual warning message system on the windshield as a head-up display to communicate the presence of a conflicting, non-connected running red light runner to a connected vehicle. And we had 4 different locations of the activation of the warning system and the stop bar pavement marking, 50 feet, 100 feet, and 150 feet before the pavement marking stop bar. And drivers reacted differently. They reduced their speed. Some came to a complete stop. And based on all the results we had, on all the data we had, we suggest having a warning system activated at 50 feet or 100 feet before the stop bar pavement marking. Any questions?
So Hiba, what is next? Do you have any planned follow-up studies or other studies ongoing?
Yeah, so Madison is a beta test for connected vehicles, and we're planning on testing this on field. So we did the warning message system in the driving simulator, so we'd know when to or like where to activate this system. And then we wanna test it on field and check that everything is working. So this is our next step.
Thank you. For the earlier warnings farther away from the intersection, did you notice participants waiting to respond at a certain point?
So when we had the warning system activated at the 100 feet, so what happened, sometimes they, like for the first couple of seconds, they don't see anything, so they don't react. So they would actually react as if the warning system was activated at the stop bar, for example. So they would react too long, if I want to say.
So here's a follow-up question to the previous one. Would you say they were waiting until they could see the threat?
So they didn't wait. So they didn't reduce their speed or come to a complete stop the moment they saw the warning system. They sometimes they reduced their speed a little bit, and then they continued reducing their speed until they saw the red light runners. Some of them they didn't care about the warning system. So, but in general, they did reduce their speed once they got the warning system being activated.
Excellent, thank you. Okay, so we are a little past time. I think we will end it there. Once again, thank you everyone for joining, and thank you for the questions. Hiba, thank you for the presentation. We will send this out. It'll be online by the end of the week. And look out for our next webinar announcement. Our next presentation is Tuesday, September 24th, and that will feature research from the University of Iowa. Thank you, everyone, and we'll see you next time.